I mean, that clearly doesn't work. 3 does not divide 3n, or 3 times 2 plus 2, right? So, that's true for that value. But, if you guys were to substitute that, that's false, right? So, this is false, but this is true for that singular instance, okay? So, unfortunately, you can't just find one of them because of that. Does that make more sense now? Okay? It's valid. What you were saying is on the right track.
It's valid if you're only given the negation.
Right.
You're saying prove that true or false.
Right. Unfortunately, though. Not fortunately. Okay. Go ahead, Adam.
Okay, so just to make sure, so,
Do we go back?
sure,
Okay.
that when, we'll just say that if you have a normal proof, like just saying if it's true or not, and then you have a contrary positive, one has to be true and one has to be false. And
For
then-
contradiction. Right. Not contraposition. So I think you might have accidentally said
Yeah,
contradiction. But for contradiction, only one is true and only one is false. They both can't be true and they both can't be false. One must be true and one must be false.
So will there ever be a case where one of them is true and the other one is true?
No, sir. Cannot be.
So
Okay.
that would never happen.
Correct. It is impossible logically. Okay? And in fact, like go back to this. Right? The negation of that. The original statement is either true or false. And that's the definition of a statement. So the very first definition we ever put up in class is a statement is a sentence that's either true or false, but not both. So it's either going to be false or true, right? So it has to be that. So it cannot both be true, it cannot both be false. It has to be one or the other. Does that make sense now as to why that is?
Yeah.
Okay, yeah, that's like fundamental to the beginning of the class. I'm glad you brought that up. Okay, other questions, guys? Okay, let's take a look at this last animal here. Okay, and I think this is one of the most powerful methodologies of indirect proof is being able to work with irrational numbers. Because we haven't worked with irrational. We've worked with integer, we've worked with rational, nothing with irrational yet, because there's no definition for irrational. Alright, so for all rational numbers x, if there's an irrational number y, then a rational times an irrational is irrational. Okay? Let's just think to see if this is true or false. Okay? So, somebody give me a rational number and an irrational number. Just give me like two numbers.
2 pi.
2 times pi, right? So, 2 is a rational number, pi is an irrational number. So this is q, this is I. And guys, we know that 2 pi is irrational, right? If I said something like maybe the opposite of 5e, okay? You guys know that that is irrational, right guys? So it seems like the product of a rational and an irrational is irrational. So it looks like the original statement's true. Let's prove it.
Can I ask you a question? Like, why is pi considered irrational? Because pi is considered the circumference over the
It's
radius.
the ratio of the circumference to the diameter,
So-
or of the circumference to the radius. right?
Radius. Then why? Isn't that the ratio? That's the ratios. Then why is it still considered irrational?
It never terminates nor repeats. It's just impossible to figure out the exact number of that. Okay.
No, but ratio is considered rational number, right? Ratio, any number that has a ratio.
Well, no, you're defining. You're thinking of ratio versus rational. Okay.
Okay.
Like for instance, that's a ratio, right?
Uh-huh.
That's not rational.
Oh.
So there's a difference between ratio and rational. They're very close, but they're not the same thing. Okay, does that make sense, Art?
Yeah.
Okay,
Yeah.
all right. The discussion for pi is a completely different class. So, anyway. All right, let's knock this out. All right, let's define our two variables x and y. Okay, so let's suppose not, first of all. Okay. What do you guys think the negation of this would be?
So that is, there exists x, basically there exists x in the domain Q such that y, what's that, the same thing, domain
Same
irrational?
thing.
So not x, y is not irrational.
Is not irrational. And
Yeah.
so remember guys, there exists some x, or we could just say that the negation of this, suppose not. Let's say suppose there exists x in q, y in I, such that xy is in what domain? Is not
Not.
irrational or
Rational.
is rational, right guys? Because that's what not irrational means. So such that xy is an element of the rationals. I'm going to put this in brackets. So q is the same as not odd. Okay, that makes sense. I mean, if it's not irrational, it must be rational. Okay. All right. So that's somewhat helpful. Okay. What can we say then? I mean, are there any definitions that we might be able to utilize?
Yeah, then x, y equals to a over b, c
Okay.
over d, like that.
Yeah, and could we also say that x is rational? So couldn't we say, by definition of rational, we could say two things. We could say that x is equal to a over b, right guys?
Mhm.
And we could also say that what? xy is equal to c over d, right? Because both of those structures are indeed rational, right guys?
We didn't define y to be
What's that?
don't you need to define y?
No, y is irrational. Did we define y to be irrational?
Oh, okay.
We don't have a definition for irrational. Does that make sense, Art?
Okay.
Okay. Can't define it if it doesn't, or we can't use a definition if it doesn't have one. Okay. And of course, we have to say what about a, b, c, and d? They're integers. C and d, or b and d are non-zero. Okay. So we're going to say a, b, c, d are integers, and b, comma d non-zero. Okay. So I'm feeling that so far. And then,
So we need to do the multiplication and see.
but what multiplication, sir?
Oh no, sorry, we need to substitute.
Substitution, right?
Yeah.
Because guys, don't we already know what x is?
Yeah.
Couldn't we substitute back in for x? So we could just plug this a over b back in for x. I don't think anyone doubts that, right guys? So by substitution, we can say that xy equals c over d. Let me erase that. Sorry. Oh, that's helping a lot. Done. Is going to be the same thing as what, guys?
CD equals to c over d times a over b.
Not CD, but you're
C-
close.
C over d, right? xy. You have to substitute the value of x is a over b, right?
A over BY. Okay, so A
A
divided
over.
by B times Y is equal to C over D, right? Does that make sense to everybody, guys? We just plugged in for X. Okay, maybe I just didn't say the question correctly. Okay. So what? How does that help us? Or maybe it doesn't help us. So, anybody have a suggestion to perhaps how we can encounter a contradiction?
We could solve for y.
We could solve for y, right? I mean, you could solve for a, you could solve for b, but I like solving for y. I really like your idea. Michelle, how did you solve for y? Or you just wanted me to do that part because that was
Well,
easy?
you can just multiply both sides by b over.
Yeah, multiply by the reciprocal. Very nice. Should work in the learning center. I'm glad some people got that. That was pretty funny. I'm funny for that.
You're
I'm not.
medium, Chris.
Yeah, I know. Okay. Guys, everybody agrees with that, right? You just multiply both sides by the reciprocal to be able to clear out a fraction. Okay? So y equals cb, or c over d times b over a. Okay, that's just by multiplication. Nobody doubts that. Okay, so what? How does that help us? Maybe it doesn't, I don't know. So,
It shows that, well, y would have to be rational over technically.
because what do you know about c times b, John?
It has to be rational.
It has to be an integer, right, you were getting it, you knew what it was. Good. Guys, don't we know that c times b is some integer value by closure, right? Let's call it p. How's that sound? Why not? So, let me actually make this a little higher so we can see what's up. Okay. So this means that y is equal to p over q, right? Just by closure. So p is an integer, q is an integer, and that's by closure.
And Q is not equal
Yeah, q is non-zero. Might as well throw it in there. It's not essential nor detrimental to the proof, but you are correct. All right. John, what were you getting at when you were saying that? You're absolutely right.
PQ has to be rational, but Y is supposed to be irrational.
That's a contradiction. Very nice, sir. Guys, didn't we at the very beginning of the proof define y to be irrational?
to.
But isn't p over q the very definition of rationality?
Yes.
Go on. No good. Contradiction. Okay? That's our contradiction at that point. Okay? So thus, y is rational by definition of rational. Okay. But y is an element of the irrationals. Okay. That's like saying a number is both even and odd at the same time. There is no number that's both even and odd at the same time. Okay? It's either got to be even or odd. It's either got to be rational or irrational. Can't be both. Okay? Thus, negation's false, original's true. We got it. Okay? So thus, our negation is false, and the original is true. And of course, whatever you put in brackets doesn't count. Blue jays suck. Alright. If you guys want to put that as a comment in there, that's fine.
So is there a negation of blue jay suck?
Yeah, blue jays do not suck. But obviously, remember, with any statement, only one's true and the other one's false.
False.
So obviously, it's true that the blue jays suck.
Will we get extra credit if you put that?
I'll tell you what, if you don't put it, I might take all points. Alright, no, I'm just kidding, they don't suck, they're actually pretty good. Okay, guys, questions I can answer about contradiction. Okay, so the ones I showed you, these are the main methods I'm going to ask you guys to do. I'm not going to throw anything tricky in there, but there are literally thousands of contradictions that you could encounter. I just showed you guys some elementary types. Okay? Much easier is contraposition. Okay, so let's just go ahead and do maybe
So
a proof or two.
contradiction has nothing to do with converse, right?
No, sir, no.
Okay. That's what I was making the mistake.
Right, converse is completely different.
Okay.
Okay, let's say for some reason you have an odd integer, and it's a square. It's a perfect square and it's odd. That means that its square root must also be odd. Okay? Now, remember, this is only true for perfect squares. We want to prove this for any sort of perfect square that's odd. Its root must also be odd. So, somebody tell me a perfect square that's odd, please.
One-
A perfect square.
169.
169, that's fine. Okay, so 169. That's an even one, bro. Come on. I got it right. Okay, but so this would be n squared, and then this guy is n, right? And obviously that's the odd. And you guys can do the same thing with 1 as well. Okay, but you could actually prove the same thing for even as well. The square root of a perfect square that's even is also even as well. Okay, so guys, it looks like it's true, right? I always like to just show it's true, just so you guys believe me before we do it for all. All right. Now, we are not going to do this by contradiction. We are going to do this by contraposition. So the first thing we need to do is write the contrapositive, right? So, if I was to ask you guys, what is the contrapositive of this statement? Okay, and I'm going to put this in brackets. Okay, so this is the contrapositive. For all n in Z.
If n is not a member of Z odd, then n square is not a member of Z odd.
Okay, so
You can just say that L is even.
okay, there we go. So, if n is not a member of Z odd, then n squared is not a member of Z odd. Okay? Remember what contraposition says? Contraposition says that you flip the antecedent predicate and you take the negation. Or, as somebody else was just saying, what's another way that we could write this? If n is even, then
n squared is
n squared is even. Nice, Greg. Alright. So, another way to write this is to say, if n is in z even, because it's either even or odd, then n squared is in z. Does that make sense, guys? All we did was we just flipped it around and we took the negation of it. Guys, isn't this a proof that we could have done the very first time we looked at proofs with direct proofs? Okay, this is about as easy as it gets. Okay? So, let's let n be an element of z even, because we're trying to prove the contrapositive valid. And we can all easily do this, I feel. Okay, so, let's let n be an element of z even. Okay? Because all we're trying to do is we're just trying to prove the contrapositive to be valid. Okay? Well, guys, if we know that n is in z even, what does that mean?
n equals 2k.
N equals 2k, where k is an integer. Nice, Greg. So, by definition of even, n is equal to 2k, k is an element of the integers. Okay, I'm feeling that. Once we use the definition of even, okay, what's the next thing we should probably do? Substitute, right? Nice. Guys, every time we have even and odds, it's almost like substitution has to be the next step. Okay, so by substitution, what are we substituting into? N squared. Nice, thank you. So by substitution, n squared is equal to the quantity